Hello everyone, we are the team Pixel from Shah and Anchor Kachi Engineering College. Our project focuses on the critical problems in semiconductor inspection, restoring degraded and low resolution inspection images while preserving the actual information present in them. Our team consists of myself, Aditya Madvi, my friend Hazik Lange, Smith Patil, and Shivam Sangpal. Our project focuses on a critical problem in semiconductor inspection, that is restoring degraded and low resolution inspection images while preserving the actual information present on them. Our core principle is simple, that is in semiconductor inspection an image should not just look better, it should remain faithful to reality. The problem statement. So let us now understand the problem statement. Semiconductor inspection requires extremely precise visualization because defects can be extremely small. An inspection image can go through multiple types of degradation such as Gaussian noise, speckle noise, and downsampling. The challenge becomes even harder because the order of these degradation may be unknown, and multiple degradation can occur together. For example, an image may need to be restored from 128 into 128 to 256 into 256 or 256 into 256 to 512 into 512. But simply increasing the resolution is not enough. If the model generates a details that were never actually present, it could potentially create a false defect. Therefore, our problem statement is not simply to image enhancement, it is faithful image restoration. Moving on to Hazik.
Understand the idea description. To solve this problem, we propose a degradation-aware residual 2x restoration network. Our approach combines a stable reconstruction path with a learned restoration path. First, the bicubic path preserves the global geometry of the input. Then, our CNN-based residual branch learns the missing details and predicts the required residual correction. This means that the neural network is not asked to completely recreate the image from scratch. Instead, it starts from a stable geometric reconstruction and learns what is actually missing. Our model uses 48 features, channels, 8 residual blocks, and 2x pixel shuffle upsampling, producing a single grayscale output. The architecture is intentionally lightweight to support practical interference. Proposed solution. Now let us look at how the solution works as a complete system. We begin with paired data, degraded images, and a corresponding ground truth images. We prepare the supply and apply controlled degradation such as noise and downsampling. The degraded image is then passed through our restoration network. The model performs denoising and super resolution together and produces a 2x full resolution reconstruction. Finally, we compare the reconstruction with the ground truth and validate the quality of restoration. So, our pipeline can be summarized as paired data goes into degradation, then restoration, then 2x reconstruction, and finally validation. Now, Smith Patil will continue from here on.
So innovation and uniqueness. What makes our solution different? Our primary innovation is integrated restoration and anchored by geometry. Traditional enhancement can focus heavily on making an image look sharper or more realistic. But for semiconductor inspection, that approach can be risky. We instead use the stable bicubic part to preserve global geometry, while the learned residual branch focuses on recovering missing information. This gives us the more control on restoration process. We also do not assume a fixed degradation order, and our approach jointly addresses denoising and super resolution. Therefore, our competitive advantage is not simply producing a high resolution image, it is producing a high resolution image while prioritizing structural fidelity. Now, to impact and benefits. The impact of a solution is centered around one goal: better inspection input without fabricated results. A more reliable restored image can help downstream inspection system better analyze small structure. But we do not want to claim that image is better simply because it looks better. We evaluate the reconstruct quantitatively. PSNR measures the pixel level reconstruct fidelity. SSIM measures structural similarities. LPIPS measures perceptual reconstruct differences. And latency measure practical inference performance. For feasible perspective, our implementation uses standard PyTorch, requires no custom hardware, can be trained using a single GPU, and provide a reproducible inference pipeline. If asked about a benchmark status, the official benchmark value will be inserted after final training and validation, so we are not presenting unverified performance and numbers. Handing over to Shivam. So now we will be speaking about technology and feasibility. For the implementation perspective, our solution is built using a standard deep learning technology stack. The core model is implemented using Python and PyTorch. Image processing and dataset preparation can be handled using tools such as OpenCV and NumPy. The model follows a residual learning architecture with a stable bicubic path and 2 times upsampling. For training, we use the CUDA-enabled GPU wherever it is available. Importantly, the solution does not require a specialized or a custom hardware. Our methodology covers the complete cycle: dataset preparation, regression and simulation, and model training, interface, and quantitative evaluation. This makes the system reproducibly and feasible to develop using a commonly available machine learning infrastructure. Now, to conclude our project, this project addresses a very specific but important problem in the semiconductor conductor inspection. We are not trying to create the most visual impressive image. We are trying to create a trustworthy restoration. Our approach combines a stable geometric reconstruction path while regression-aware residual learning to recover lost information while preserving the actual structure of the image. We will validate the model using objective metrics such as PSNR, SSIM, LPIPS, and inference latency. Ultimately, our vision is simple: restore what was lost, preserve what was real, and avoid inventing what was never there. Thank you.